us apply R-H stability criteria to some of the problems, and the requirement here is a characteristic equation to assess the stability using this criteria. So, let us see the characteristic equation. It is of third order, then s power 3 plus 6 s square plus 4s plus 6. Find out the stability using R-H stability criteria. You can see that the necessary condition is met here because no term is missing and all the coefficients have same sign. Now, we need to form the R-H table for this simple third order system, starting from highest power of s, then next highest. So, first two rows, as I said, to be formed from the given data, s power 3 1, then coefficient of s, alternate terms, and next s square coefficient is 6 and alternate term is again 6. So, first two rows are to be formed from the given equation. Now, s power 1 up to s power 0, you have to continue the table. So, when the row has elements which are divisible by a common number, you can divide it. So, the 6 and 6, so I can divide by 6, so I get 1. That can be done for simplification. Now, see here 4, 1 into 4 minus 1, 4 minus 1, 3. So, this is the first element. Now, the s power 0 I need to get. So, there is no other element here, simply you assume 0. So, 3 into 1, 3 minus 0 by 3. So, you will get 1. Product of these two numbers and minus product of these two numbers divided by the first element of the previous row. So, you can see here now the first row has 1, then 3 and then 1. So, all the elements in the first column are no sign change. So, we say that it is a stable system. That means all the three roots of this equation lie in the left half of the S-plane. So, system is stable. Now, let us see the second problem. S power 4 plus 2s cube plus 3s square plus 2s plus 1 equal to 0. Find out the stability using R-H stability criteria. Now, it is a fourth order system. So, as I indicated, we must begin with the highest power of s and second highest. The coefficient of s power 4 is 1, alternate terms coefficient 3 and then 1. For s power 3 row, the coefficient is 2 and alternate term 2 and 0. First two rows are formed from the characteristic equation, and then you have to continue the rows until s power 0 row is obtained. So, 3 into 2 6 minus 2 4 by 2, so it is 2, and 2 into 1 2 0 by 2, so it is 1. Now, s power 1 row product of these two 4 minus 2 2 by 2 1, and this is anyway 0, and s power 0 is product of these two 1 0 by 1, so it is 1. You can always observe that the element here, last element of s power 4 the row will be followed in s power 2 row, then again in the s power 0th row. You can always cross check whether you are doing right or wrong. This way, the last component of s power 4, s power 2 and s power 0 will be same. Now, you can see that all the elements in the first column of the Routh's array have no sign change. So, the system is stable here. Problem number 3, as cube plus bs square plus cs plus d equal to 0. Find out the stability of the system using R-H stability criteria. When third order system is given, like as cube plus bs square plus cs plus d equal to 0, whatever may be the example, you need not create the Routh table, and you can get the answer quickly by looking at the coefficients of the given function. Let us see, if it is a general equation of third order given like this, then R-H table, as you know, it is created in the similar way explained before. The coefficients of s power 3 is a, alternate term c, and for s square the coefficient is b and the constant is d. So the s power 1 and s power 0 are the remaining rows. So this is bc minus ad by b is the element in the s power 1 row, and here s power 0 is product of these two minus product of this by this component. So this d will simply come here. Now for stability, remember that this component, if you take bc minus ad by b must be greater than 0, that indicates bc is greater than ad for stability. And I say that if this happens, I say that system is stable. Suppose if bc is less than ad, the coefficients, you can directly look at them. If third order is given, you need not create the right hand R-H table, but by looking at these coefficients, if product of bc is greater than product of ad, product of bc is greater than product of ad, then we say that it is a stable system. If this happens like bc less than ad, then you can say that it is an unstable system. Means you will definitely get some roots lying in the right half. That means there will be some sign changes in the first column. So if this happens bc less than ad, we say it is an unstable system, and if it is bc equal to ad, it is a marginally stable, means at the verge of instability. So bc equal to ad is a marginally or critically stable system. Let us see some examples of third order system where by looking at the equation itself, you can say that whether the system is stable or unstable. Fourth problem, characteristic equation of a system is given by s power 3 plus 8s square plus 9s plus 10 equal to 0. Find out the stability using R-H stability criteria. This is the system characteristic equation. So this is nothing but 1 plus g of s into h of s equal to 0. So roots of such equation are known as poles of closed loop transfer function, and such poles must lie in the left half for stability. Now as I indicated in the previous example, that you need not create the Routh table, just look at the coefficients of this one. You can just compare this with this, as cube plus bs square plus cs plus d equal to 0. So for stability, bc, this product of these two, that is called bc, must be greater than ad for the system to be stable. So 9 8s are 72, that is bc. Now ad, this is a coefficient 1 and d is 10, so you get 10 as ad product. So 72 is greater than 10. So even if you create R-H table, definitely the first column of that table will have no sign change. So it is known here itself. So 72 is greater than 10. So I say that this given characteristic equation is a stable system. If I change the coefficients, for example, s power 3 plus 4s square plus 8s plus 100 equal to 0. You can look at this. Now I have changed the coefficient slightly, that b and c product 4 into 8 is 32. and the product of A here is 1 and D is 100. So product of AD is 100. So 32 is not greater than, but 32 is less than 100. So that means BC is less than AD. So this is an unstable system. So definitely one or more roots of this equation will lie in the right half of the S-plane. So you are not creating the table here, but you are able to assess using the coefficients directly that BC must be greater than AD for stable. If BC is less than AD, it is an unstable system. For example, if you have S power 3 plus 4s square plus 8s plus 32 equal to 0, then this is 1. So coefficients of BC is 32 and coefficients of A and D is also 32. So both are same. That means BC is equal to AD. So it is marginally stable system. Marginally stable system. So this is the way when third order system is given, you can assess the stability without actually going for R-H table. Fifth problem, the characteristic equation of a system is given by S power 4 plus 2s cube plus 3s square plus 4s plus 5 equal to 0. Find out the stability of such a system using R-H stability criteria. So for this, as you are aware that S power 4 and S power 3 rows are to be formed from the given characteristic equation 1, 3 and 5 and 2, then 4 and then 0. Now you need to obtain S power 2 row from this. 2 3s are 6 minus 4 2 by 2. So you get 1 here, and the next element is 2 into 5 10 minus 0 by 2. So it is 5. Now S power 1 row is product of these two. 4 minus 10 is minus 6 by 1. So it is minus 6. Now S power 0 row, you can assume here 0, and then product of this you get 5. So you can see one observation whether the table formed by you is right or wrong by looking at this last element of S power 4 row, same as S power second row, and this is again same as S power 0th row. That is one information that you have done right way. Now look at the first column of the elements. First element is 1, then 2, then 1, minus 6 and then 5. So you know that they all have plus sign and this is also plus. So there is one sign change here from plus to minus and another sign change from minus to plus. So I can say that there are two sign changes in the first column. There are two sign changes in the first column, indicates that there are two roots lie in the right half of the S-plane. Two roots or two poles out of fourth order. This is fourth order system. So there are two poles in the right half and the remaining two poles, total 4. So 2 poles in the right half and 2 poles in the left half of the S-plane. So even one or more poles lie in the right half, system is unstable. So the conclusion here is it is an unstable system. So this is the information you will get from R-H stability criteria. Even if it is an 8th order or 10th order equation, the stability can be assessed in a very simple way that only focus on first column of the routes array. Number of sign changes indicates that many poles lying in the right half out of the total. So system is unstable. Sixth problem, the characteristic equation of the system is 2s power 4 plus s power 3 plus 3s square plus 5s plus 10 equal to 0. Find out the stability of the system using R-H stability criteria. Problem on R-H stability criteria. Equation is given and we need to form the R-H table for this. You need to write the coefficients of s power 4, 2, then alternate terms 10. For s power third row, the coefficient of s power 3 is 1 here, then alternate terms 5, no element, so it is 0. Now s power 2 row, 3 minus 10, so it is minus 7, and 10 is the second element, and s power 1 row now minus 35, 10, minus 45 by minus 7, so it is 45 by 7, and s power 0 the row, this 10 is directly taken here, no need to calculate. Now you can see here there are two sign changes from 1 to minus 7 and the other one is from minus 7 to plus 45 by 7. So two sign changes, plus to minus and minus to plus. So two sign changes. Two sign changes indicate that two roots in the right half of the S plane, and so the system is unstable. The system is unstable because two roots are in the right half out of 4 and the remaining two roots are in the left half of the S plane. So the system is unstable. So far so good, that stability, how to assess when characteristic equation is given using R-H stability criteria. But there are some difficulties while forming the table. We call it as a special cases that appear while forming the table. So that special cases are difficulties to appear in the R-H table. How to overcome that? What is the remedy? So special cases are two, or I say that it is a difficulty. So that difficulty 1 is that while forming the table, if you get one element in the first column of any row is 0. So any element, one element of the first column of R-H table is 0 is the difficulty, because you cannot proceed further if there is a 0 appears in the first column. So what is the remedy? Remedy is replace that 0 by epsilon. Replace the 0 by epsilon, where epsilon is a small positive number or small negative number. So you can proceed further by replacing 0 by epsilon, and then you can complete the table. Later you can conclude whether the system is stable or not based on the sign changes in the first column. So this is the first remedy. When you have any 0 in the first column of any element, then replace 0 by epsilon and proceed further and complete the table. Second difficulty is that a row of zeros, not a single element of the first column, but a row, complete row of zeros that may appear in the one of the rows of the R-H table. So that is the difficulty. Then what is the remedy? So that is invented by Routs and Hurwitz, that if such situation arises while creating the table, then what you have to do is you select the row above the row of zeros. Call that as auxiliary equation. A row above zeros consider as auxiliary equation. Call it as A of S. That equation, auxiliary equation means it has a even polynomial, and the roots of that auxiliary equation are symmetrical. Now, once you get A of S, you differentiate this with respect to S, then the coefficients of that equation, differentiated auxiliary equation, coefficients of this d A of S by ds must be replaced in zeros. You have already got a row of zeros. Those zeros must be replaced by the coefficients of an auxiliary equation after differentiation. Then you continue constructing the table and complete it till you get S power zeros row. Now, what is the information you have when you get auxiliary equation? That indicates there may be a possibility of roots or poles lying on j omega axis. So, a row of zeros existence in R-H table is the indicative of some roots lying on j omega axis, indicates that the system is marginally stable. So that information also you get from R-H table, that if any roots lying on j omega axis also can be determined. And also once you are able to determine such roots, you can also determine the frequency of oscillations of a given system also can be determined from this R-H table. Problem 7. The characteristic equation of the system is given by s power 5 plus 2s power 4 plus 3s cube plus 6s square plus 5s plus 3 equal to 0. Find out the stability of the system using R-H stability criteria. Let us look at the fifth order system given here. For this you need to form the R-H table. Then s power 3 row 6 minus 6, so you get 0. Then 10 minus 3 is 7 by 2, you get here the second component. So there is one element 0 in the first column. You cannot proceed further to complete the table anymore. So you need to replace this 0 by epsilon, a small positive value or negative. Now you can just see here, this is 6 epsilon minus 7 by epsilon. This is the element of s power 2 row. Now the second element of s power 2 row is 3 epsilon by epsilon, so you get 3. Now s power 1 row is by using these two. You should get s power 1 row as minus 7 by epsilon into 7 by 2 minus 3 epsilon by minus 7 by epsilon, assuming epsilon is a small value, and finally s power 0 as 3. So you can see here there are two sign changes. So from here to here one sign change, and from here to here there is another sign change. So the number of sign changes are 2, indicates roots in right half are 2. So out of 5 there are 2 roots in the right half and the remaining 2 roots are in the left half. So the system is unstable. So it is an unstable system. That is the conclusion. Problem 8. The characteristic equation of a given system is s power 4 plus 2s cube plus 5s square plus 10s plus 5 equal to 0. Find out the stability using R-H Stability Criteria. So let us consider that s power 4 and s power 3 rho, as usual we have discussed in the previous problems, 1, 5 and 5, then 2, 10 and 0. So as I indicated, if entire row can be divisible by some number, you can do that for simplification. So this I can say it is 1 and this is 5. Now s power 2 row we need to obtain product of this 5 minus 5, 0 by 1, so it is 0. Second component of s power 2 row is 5 minus 0 into 1, 0 by 1, you get 5. So same 5 is to be get here. That means your approach is right. Then s power 1 row, to obtain this you can't do this product because there is a 0 in the first column. When it comes in the denominator it becomes infinite. So this 0, to continue the table till s power 0th row, replace this 0 by epsilon. Now you continue constructing the table. So this is the case 1 which we have discussed just now, that if there is a 0 appears in the first column, one element is 0, then replace it by epsilon, then continue constructing the table. So 5 epsilon minus 5 by epsilon. So 5 epsilon minus 5 by again epsilon, and this s power 0th row, product of this you can assume 0 here, product of this divided by this. So as it is, this 5 comes here. This is the way you should complete the table. Now let us look at the first column. We are not interested in the values, but we are interested only in the sign changes in the first column. So the first element is 1, second element in the first column is 1, third element is epsilon, and fourth element is 5 epsilon minus 5 by epsilon, last element is 5. I can assume now epsilon is 0, no problem, that this epsilon is 0 or a small positive value, doesn't matter, because value is not important, sign changes are important. So when I say epsilon is 0, this will be infinity, you get anyway, and this is 5, this is 1 and this is 1. So the no sign changes you observe in the first column. So system is stable. System is stable, but only thing is, to construct the table you have replaced 0 by epsilon. So even if you consider epsilon as a small positive value, epsilon as a small positive or small negative value, and then you can complete the table. If you don't want to look at the infinity in the first column, you can do this a small positive value, maybe 0.001 or minus 0.001, doesn't matter. You can replace it, that epsilon value, substitute it, and if you find any sign changes, then system is unstable. But as far as this problem is concerned, the system is stable because no roots are lying in the right half because no sign changes. The characteristic equation of a system is given by s power 6 plus 2s power 5 plus 8s power 4 plus 12s cube plus 20s square plus 16s plus 16 equal to 0. Find out the stability of a system using R-H stability criteria. So the given equation, you can see it is of a 6th order. So very complex equation, 6th order, very difficult to solve, difficult to find out the roots using normal procedure. But R-H stability criteria made us very simple to assess the stability even it is a 6th order system. Let us see what is the status of this particular system according to this criteria. Starting from s power 6th row, then second highest s power 5. You need to form the table. This is called R-H table. So how to choose s power 6 row elements? From the given characteristic equation, start from coefficient of s power 6. It is default 1, then 8, then 20, then 16. Alternate elements. Start from highest power, then alternate terms coefficients must be written in the first row. Second row, start from the second coefficient, that is 2, and choose again alternate terms 12, 16, and then no element, you can just put 0. So as I indicated that this entire row can be divided by same number for simplification of our approach. So divide this by 2, all 3 elements by 2, you get 1, 6 and 8. Now we need to form s power 4th row by using this product. 8 minus 6 by 1 is 2. Then 20 minus 8, 12 by 1, 12. So 1 into 16 minus 0 divided by 1, so it is 16. So again you can use, for simplification, divide this entire row by 2, you get 1, 6, 8. When you observe s power 5 and s power 4th row elements, now 1, 6, 8, 1, 6, 8. So certainly the s power 3 row, if you want to get now, you get entire row of zeros, because product of this is 6 minus 6, 0 by 1, so you get 0. Similarly, the second component of s power 3 row is also 0, because product of this 8 minus 8 is 0. So I say that this is a row of zeros. A row of zeros. Second difficulty in R-H table is a row of zeros. So you cannot go further, but what is the indication here? When you get row of zeros, certainly among these 6 roots, few roots lie on j omega axis. So the system is marginally stable. You can conclude here itself whether the system is stable, unstable or marginally stable. You can say by looking at the row of zeros, the system is marginally stable, because out of 6, few roots will lie on j omega axis. So now once you get this row of zeros, you have to choose an auxiliary equation. An auxiliary equation from the coefficients above the row of zeros. So that means A of s is s power 4th row. So s power 4th row, you see the components 1, 6 and 8. So s power 4 plus 6 s square plus 8. This is a auxiliary equation. You can see that it is a even polynomial. Only even power coefficients exist. Now the poles or roots of this equation will be symmetric. So once you get auxiliary equation, you have to differentiate with respect to s. So this becomes 4s cube plus 12s. So the coefficients of this equation, you need to put them here in place of zeros. So this 0 is replaced by the 4 and this 0 is replaced by 12. Now you need to continue constructing the table. S power 2 is, you can see here 4 and 12 can be divisible by 4. So you can just make it 1, this 12 as 3. So now product of this 6 minus 3 is 3. So you have an element 3. Now the third component here is 8 and there is no component, you can assume 0. So this is 8 minus 0 by 1. So you get 8. Next, s power 1 row, that is 3 into 3 9 minus 8 is 1 and 1 by 3. So to get s power 0th row, you can assume here 0 and the product of these two product minus divided by this component, you will get 8. So this is the way you should approach R-H stability criteria when you have a row of zeros in this way. Now you can look at the first column of the Routh's array, no sign changes. So no doubt there are no poles in the right half, because conclusion, no sign change in the first column. So no poles in the right half of the S plane, but a row of zeros indicate that there are some roots lying on j omega axis. So it is a fourth order auxiliary polynomial. So there are 4 roots or 4 poles lie on j omega axis. So this indicates the system is marginally stable. So out of 6 here total, 4 roots are lying on j omega axis, that is from the auxiliary equation. So the remaining 2 roots will be definitely in the left half. So the system is critically or marginally stable. Now I would like to know where these poles are located on j omega axis, the location. So for that, you can just have this equation, auxiliary equation, s power 4 plus 6 s square plus 8. Now put s square is equal to x, then the auxiliary equation becomes x square plus 6x plus 8. So the roots of this equation are minus 2, minus 4. That means, as you know that x is equal to minus 2, but I want to know s only. So there are 4 roots here, s is equal to plus or minus root 2 j, and the another 2 roots are plus or minus j 2. So what does it mean? That in the S plane, complex plane, one pair having j root 2 minus j root 2, the another 2 roots are j2 and minus j2. So out of 6, 4 roots are lying on j omega axis. So system is marginally stable. So the conclusion is the given system is marginally stable. This is the conclusion of this particular problem. The difficulty 2 has been arised while forming the R-H table. the remedy is get auxiliary polynomial, differentiate it, and zeros are replaced by the coefficients of this, continue constructing the table, and this is the way you should find out the location of poles on j omega axis.